Hello everyone, welcome back to my channel. Today we are going to explore a very interesting and slightly advanced coding problem where we learn how to partition a string into multiple parts while keeping track of unique character, and even get a special twist. We are allowed to change one character to get the best possible result. We will solving this using recursion, bit masking and memorization for optimization. So let's dive in and break down the code step by step. Okay. So the question title is maximize the number of partition after operation. Here is the question. You can see on the display bar, that is on the display bar, and here is the constant 2, that is 1 is less than equal to s dot length less than equal to 10 ki power 4. Second point is yes consists only on of lower cases English letter, and one is less than equal to k and less than equal to 26. Okay, so first of all we have just take a small time and just reading the question, that is you are given a string yes and integer k. First you are allowed to change at most one index in yes to another lowercase English letter. After that, do the following partitions operation until yes is empty. Choose the longest prefix of yes containing at most k distinct character. Okay. Delete the prefix from yes and increase the number of partition by 1. The remaining character, if any, in yes maintaining their initial order. Returning an integer denoting the maximum number of resulting partition after the operation by optimally choosing at most one index to change. Okay, we will just take a one example, nothing more than that. Okay, so here input is equal to yes is equal to what? A triple C A, and k value is 2. Okay, and output will be 3. Explanation, that is the optimal way is to change yes to something other than A and C. For example, B. Then it becomes ACBCA. Okay. Then we perform the operation. The longest prefix containing at most two distinct characters is AC. Okay. So we remove it and S becomes BCA. Second point is now the longest prefix containing at most two distinct characters is BC. So we remove it and S becomes A. And third point is finally we remove A and S becomes empty, so the procedure ends. Okay, doing the operation, the string is divided into 3 partitions, so the answer is 3. Okay, we will just take an example 2 and 3, and we will not take so much time, and let's dive into the question. Okay, so here we are solving this question using Python language. Okay, because I am just a Python developer. Okay, so in the first line, class solution, here we start by defining a class named solution. This is a common pattern in LeetCode style problem. This is a common pattern in LeetCode problem where the main logic is wrapped inside a class. Okay. In the second line, def max partitions after operation self comma yes comma k. Here we define a function maximum partition after operation which like takes two parameter yes and k, which is a display on the display, that is yes, where yes is equal to what? A string containing lowercase letter, and k is what? An integer that represent the maximum number of unique character allowed in a partition. Okay, now we come to the line 3, that is n is equal to len yes. We calculate and store the length of the string yes in variable n. Okay, now come to the line 4, where memo is equal to comma. Okay, so here we create a dictionary named memo to result of already computed subprogram for memorization. Okay, as we talked previously that we will use the memorization concept. This help us avoid recalculating the same state and improve efficiency. Okay, now come to the line 6. Okay, so def solve I comma unique char comma can change. Here we define a recursive helper function solve which takes 3 parameters. First parameter is what? I. I is what? The current index in the string. Now unique character, what is that? A bit mask representing which character are currently in the current partition. And the third one is what? Can change. Here a boolean. Boolean means what? True or false, indicating whether we are still allowed to change one character in the string. Now come to the line 7, that is key is equal to I comma unique char comma can change. Here we create a tuple key representing the current state of recursion, index comma set of character comma and whether we can still change a character. Okay, now comes to the line 8 to 10. Okay, we will take one part, that is if key in memo return memo key. If this state has already been computed and stored in our memo dictionary, we immediately return the saved result instead of recomputing it. Okay, now comes to the line, just wait for 1 second. Okay, yes, so here come to the line 11, if I is equal to n, return 0. So here we have reached the end of the string, there are no more partition to make, so we return is equal to 0. Now comes to the line 14, here we have write there character index is equal to odd si minus odd a. Okay, so here we find the index of the current character from 0 to 25 by subtracting a from the ASCII value of a character is yes is equal to I. Okay, now comes to the line 15, updated set is equal to unique char and I is less than character index here. So here we add the current character into our bit mask unique char by turning on the bit corresponding to char index. Okay, now turn to the line 16, unique count is equal to bin updated set comma count 1. Here we count how many unique characters are currently in our set by counting how many bits are set to 1 in the bit mask. Okay, now comes to the line 18 to 20. Okay, if unique count is greater than k, race is equal to 1 plus sol I plus 1 is less than char index comma can change, and we have taken also a condition that is else. Okay, race is equal to sol I plus 1 comma updated set comma can change. Okay, so now if the number of the unique character exceed the limit k, we start a new partitions here, adding 1 to the result for starting a new partition. We set the unique set to containing like only the current character, otherwise we are still within the limit, so we continue adding this character to the current means partition. Okay, now come to the line 22 to 28. Okay, now come to line 23, like we start right, so if can change for new index in range 26, that is 0 to 25. Okay, A to Z. Okay, so new set is equal to unique char, 1 is less than new index, new count is equal to bin new set dot count 1 if new count is greater than k, and race is equal to max race comma 1 plus solve I plus 1 comma I is less than new index comma false. So here we define this section explore the word change one character option. If we are still allowed to change can change is equal to true, so we will just change the can change value booleans to like true to false. We tried 3 options. First is we try changing the current character yes I to every possible letter A to Z. For each possible change we updated the bit mask. Okay, then we check if the new character makes the unique count exceed k, we start a new partition, otherwise we continue in the same partition. We use what max race to store the best possible maximum partition result. After this step can change become false because we have used our one allowed modification. Now we comes to the line 30. Okay, that is race is equal to max race comma solve I plus 1 comma new set comma false. Okay, so before returning we save the compute result for this state in the memo to reuse the later. Now we comes to the line return yes, return the final result for this recursive state. Now last is a what result solve 0 comma true plus 1. Here finally we start the recursion from index 0 within the empty unique set that is 0 and change allow true. Okay, we add 1 at the end because the number of partition is 1 more than the number of split. So in summary, This code recursively explore all the way to split the string yes into where each partition can contain at most k unique letter. It also allows changing one character anywhere in the string to maximize the number of partition using memorization, as we said previously. It avoids recomputation of subprogram. Finally, it results the total maximum partition possible after considering one allowed changes. Okay, so all this point has been resolved. So now this problem is more means competitive. Okay, so that's how this solution is smartly combined recursion, bit masking, and memorization to solve a challenging string partition problem efficiently. If you find this explanation helpful, do not forget to like the videos, subscribe for more coding breakdown, and drop a comment if you had liked me to dry run this code with this sample example. Thank you for watching and happy coding.